Heissenberg from IPHT, who's going to talk about gravitational waveforms and infinity at the horizon.
Thanks, and let me start, of course, by thanking the organizers for putting together this very nice workshop and inviting me to really amazing experience. It's always a pleasure to be back in Trieste, but especially in this workshop, I think I've been learning a lot. It's been very good course. So, yeah, let me start very broadly by saying that the context for this presentation is, of course, the interest in the gravitational two-body problem that is being revived now a few years due to the direct observation of gravitational waves. And, of course, it's a problem that is very easy to state, but, of course, when one then wants to end up with some concrete analytical solutions, it gets very challenging very quickly. So, the problem, very simply put, is to consider two massive objects in general relativity, so masses M1 and M2, that we consider, like many of the other talks, an asymptotically flat setup, and separated by some initial, let's say, impact parameter in the case of a scattering, or some typical separation in the case of a merger, and well, then the problem would be to see what happens. So one would like to understand if these objects deflect, if they eventually form a bound state, if they fly off to infinity. In the meantime, of course, the main interest would be to understand how much radiation they emit. So this is, of course, a very challenging problem, as I said, and one angle of attack, which is what we're going to focus on today, is to identify some small parameter which we can expand in to gain analytic control. Of course, another standpoint could be instead to use a computer, and this also means very successful, but since they have a blackboard and not a computer, let me try the first approach. So, in particular, my motivation for, well, the way how I got interested in all of this was that this system enjoys, in a specific setup that we'll review in a second, a connection with scattering amplitudes. So, what I thought I would do for this presentation to start by a very quick review of what the status is, in particular, in calculating the gravitational waveform for scatterings, mainly based on some recent works in collaboration with Alessandro Gervudis and Rodolfo Russo. But the application I wanted to focus on instead mostly today is a bit different, and instead of looking at the waveform, the waves that eventually fly off to infinity from this two-body system, we will instead look at how much radiation is sent from one object to the other one. Typically, these two guys are black holes, so that explains why I'm speaking about waveforms at the horizon. This is going to be based on recent works instead in work in collaboration with Andrea Cipriani, Francesco Fucito, Francisco Morales, and again Rodolfo Russo. So, yeah, as I said, looking for a small parameter. So one particularly, let's say, clean setup is to look at a scattering in which this impact parameter B is very large, in the sense that compared to the masses of these two objects, we are in the so-called post-Minkowskian regime. So this is the small parameter I was alluding to, M, standing for post-Minkowskian. And indeed, this is a regime that has received a lot of attention because it has been realized that a lot of observables, in particular the deflection angle, so by how much the trajectories of the two particles deflect, as well as the gravitational waveform itself, I will review in a second more precisely what we mean by that, can be recast in terms of scattering amplitude. And I think this will play a role also in some talks tomorrow, in particular the one by Fabio Riccioni, I think, and also perhaps by Riccardo Gonzo. Another possibility is to instead look at a situation in which one of the two objects is very large, has a very big mass, and the other one is just a tiny probe that, to first approximation, just moves in the geometry that is completely dictated by the heavy object, a black hole, very large, and a small mu. And this is a setup that also, of course, already features in several talks, including Manuela, Clexisi, and Rodolfo again on Tuesday. And this is, of course, the realm where it's reasonable to apply Bell-Core perturbation theory, right? Because you can regard the field that is sourced by the light guy as a small perturbation on top of the geometry. The two leading order is just say, in these talks, we are not going to include spin. This is going to be just a Schwarzschild geometry. So, yeah, the idea for the first few minutes would be to just provide you with a lightning review of of some things that have been done using this approach, in particular focusing on waveform at infinity, and then instead I would like to focus a bit more on this second setup. So let me begin by introducing what I mean by the waveform. And by the way, feel free to, of course, interrupt me at any point and make this interactive. So this is nothing but, of course, the difference between the putative exact metric of the space-time in the ideal situation in which we were able to exactly solve the system, and the flat metric is having a man of course now away from at infinity. So what I mean is that we are going to place a detector very far away from the scattering, and we are going to measure this h mu, for instance, with LIGO, since luckily we are far away from mergers and also scatterings. So to leading order, more precise, the limit we're going to take is to send the r, the distance where the black detector is placed, to infinity by keeping fixed the retarded time, which is just the time which the detector receives this signal. And okay, the detector will be also characterized by some angles, of course, from which it sees this source, so with u fixed in particular. And to leading order in this limit, the metric fluctuation, okay, we pull out a conventional factor of 4g, but by this goes like 1 over r, and then the coefficient in front of this is what usually called the waveform, w mu. And then, of course, it's up to you if you want to really write it down in terms of the retarded time of the detector, u, or if you prefer, in Fourier domain, you can press in terms of the frequency, of course, minus omega u, and then w tilde. And this n is a vector that packages the angles in the way that you imagine. So this is a characterization of the signal that would be measured by LIGO in the presence of such a scatter. And the name of the game, as I was saying, is to solve this. What does it mean? Well, it would mean to obtain an explicit, or as explicit as possible, expression for this W in terms of the initial parameters of this problem, so the masses, the impact parameter, and say the velocities of these two objects. So, particular, okay, by some convention, I'm going to denote them by minus p1, the initial momentum of particle 1, and minus p2. So, a relevant parameter is going to be the relative Lorentz factor, which is just 1 divided by the square root of 1 minus the relative velocity squared, or sometimes it's also parameterized by 1 plus p infinity squared. There are equivalent ways of characterizing how fast the objects go. So we would like to have this waveform as a function of the sigma, say, the impact parameter, and the masses. Since we are expanding in this small PM expansion, eventually the balance of the impact parameter is going to be factorizing from. So without going into much detail, what I wanted to mention is that if you really focus on this problem, we want to calculate the waveform at infinity. Maybe, I don't know, let me become infinity here. Scattering amplitudes are your friend. And in fact, there is several works, including by Ricardo here and others also, ours, that have been realized in the last few years that a convenient way of packaging the information contains this W is precisely given by amplitudes. In particular, the recipes, that is W mu, let me omit the infinity for the moment, is basically just a Fourier transform. So let me do some factors. It's just a Fourier transform that brings you from momentum space to impact parameter space. So this Ft is nothing but something that introduces this B from something that instead lives in momentum space, so it depends on some Q, Q1. And this object here can be expressed in a simple way in terms of conventional scattering amplitude that you write down in momentum space, and you can in principle think of as just being a sum of Feynman diagram that you'll learn in kindergarten. So let me be a bit more concrete maybe. So suppose you want to be humble and just want to look at the leading order contribution in this PM expansion. So to LO in PM, it's enough to put as this W mu the 3-level building block, which is nothing but a 3-level amplitude. So literally this W0 is a 3-level amplitude, in which you have these two massive objects, the solid lines that are, if you want to do non-spinning, they can be modeled just by minimally coupled massive scalars in GR and the emission of a graviton. and this is really just a 3-level amplitude. So in particular, we depend on this P1, P2, and then here is the momentum I was talking about. And if this is k, that is omega times n, omega being really the frequency of the emitted radiation and n, that vector over there. You don't even need to calculate the full amplitude. In sort of generic kinematics, it's enough to focus on a simpler regime in which this Q1 and K are very small. So in a sense, you are in a near forward limit. They are small compared to the masses, compared to Q1. So this is sometimes referred to as the classical limit or the near forward limit. And the reason for this is that essentially Q1 is dual to 1 over b due to this Fourier transform, and 1 over b is very small in this sense.
You take the external particle to be scalar, right?
Yes. So for today, no spin.
Okay. For spinning the code, I just substitute with spin.
Yeah, for spinning black holes, in the second part of the talk, there is a very systematic way, which is going to be, for instance, consider Tokowski with spin instead of, say, Redu-Miller. Here, there has been a lot of work, but the things are a bit more complicated. I think the first person to ask is Carlo, probably.
Okay. I'm not sure you saw.
But no, I mean, there are a lot of results. It's a bit more complicated. You can just, for instance, consider a spin 1 field, because, of course, the spin then should be classical. So you should, in principle, consider a large spin quantum number in such a way that h bar times the spin quantum number is a sizable classical angular momentum, and that, of course, complicates matter, as you can imagine, a little bit.
Yeah.
So,
But it can be done.
Okay. but it's been being done, yes. So, okay, what if you look at this object to leading order?
Sorry, can I ask a
Yeah,
small question? If you take, so curiosity about spinning, is the extremality bound somehow bound?
No, okay, so the way in which you do things is that, so B is going to be much smaller than GM, and the ring radius is going to be even smaller than GM, right? So in a sense, you're going to treat both in a double expansion.
So you're always small spin.
Yeah, you basically expand as A, the ring radius divided by B, and GM over B. So to leading order, this Fourier transform can so the remaining step that I'm not doing is this Fourier transform, right? So this is a very simple rational function, it's just a 3-level amplitude. That Fourier transform can be performed, but it lands you on a, so if you really stay in omega domain or frequency domain, the Fourier transform lands you in a one-fold integral representation of Bessel functions, of modified Bessel functions of the second kind, in particular K0 and K1. So it's a, let's say, semi-explicit representation. If you instead go to really time domain, U domain, you reobtain a result that you already, in fact, gotten by Kovacs and Thorne in the late 70s, where everything is completely explicit. So there is a nice explicit representation just in terms of square roots that involve the time and the relevant scales of the problem. So let's say that the problem at 3 level is solved in this specific sense. One other thing that you can do is you can re-expand. So we have another parameter to tune in addition to those I was highlighting here, which is this parameter here, the velocity. So of course it's well known that when you also go in a regime in which the velocity is small, this is the domain of the post-Newtonian expansion, so things should be simple enough because we all know the Einstein quadrupole formula, and then the representation is again much simpler. For instance, in omega domain, you end up with rational polynomials times this Bessel function, now no integrals, so now it's completely explicit the answer, and this Bessel function depends on a parameter u that, for lack of better names, I called again u. Let me try to do something like this, which is omega times b divided by b. I introduce it because it will appear also later. So very explicit. The next order has been also studied, so this would go beyond this Kovacs and Thorne result. And okay, this order, the representation of this kernel is a bit more complicated. It involves, as you can expect, a one-loop ingredient. In particular, you can write it down in terms of the real part of the one-loop amplitude corresponding to the same process, plus some unitarity cut. Let me not go into too much detail here since it's not the focus in this talk. You can take this as some cartoons stating the problem is under control, we know what the amplitude ingredients are, in principle we know So this result has been obtained explicitly. And again, the step that is intriguing is taking this Fourier transform. There have been very recent results that essentially put the result in omega domain more or less on the same footing. And this is by work by Brunello, De Angelis, Kosover. So there are again integral representations that involve some Bessel functions. And again, when you re-expand for small velocity, things become very explicit. So let me say T infinity very small. Everything is very explicit. And okay, in addition to K0 and K1, there is a K1 half, which is nothing but an exponential times some.
So U is finite.
Is this object?
But P is very small, so U is.
Yeah, thanks. Good point. Omega also scales like P infinity. Yes, this is because in the, if you want, when you do this this regime, if you send really the velocity to 0, the whole available energy would simply shrink to 0, right? Because you don't have any initial kinetic energy. So the right region of frequency to focus on to get a meaningful result is the one in which also the frequency is scaled on the same. So this is the standard post-Newtonian.
But B is big, right?
Yeah, and they are also all of the
So
in such a way. So, and omega is also, yeah, thanks for the question, in fact. The result, what does it look like? So what we are used in, let's say, the talks that talk to the general public for gravitational waves, you are used to some signal that oscillates, right? Something like this. Instead for the scattering, it's a bit different because there is only one turn, let's say, of the object. Well, what happens is that there is only one blip, something like this. And the frequency, if you do the Fourier transform, is peaked around omega over the order 1 over b. You can also see it from this function here, right? So if omega were much bigger than 1 over b, this test would be exponentially suppressed. So there is no signal. And instead, if you go to omega that are much smaller than 1 over b, this would be re-expanded in the so-called soft limit. So omega is both of order infinity and of order 1 over b.
So U is finite.
Exactly. Okay, so this is just and then okay, in principle you could go to higher orders. There is work in progress. I guess there's certain groups, but yeah, as I mentioned, this was just to provide you with a sort of bird's eye view of what can be done with amplitude in this context. And now let me instead switch to a different perspective. Well, maybe before that, just one. Yeah.
But with the amplitudes, you can also study the bounded system.
Okay, the most natural domain of application of all these techniques is the scattering, simply because it's a clean system in which you can prepare your symptotic state in such a way that they are non-interacting, freely moving. There are a series of results that allow you to analytically continue some of the results that you obtain for this unbound system-to-bound scenario. The waveform is perhaps not one of the easiest ones to do. Again, Ricardo has worked on that and others. But it's fair to say that really, if you look at the waveform, performing this analytic continuation is not the easiest thing. So before moving on, I remember I mentioned that this is generically a function of this n, so theta and phi. Of course, another possibility would be to express it as a function of L and M, so you can contract your waveform with some polarizations, plus or minus polarizations, and then project on the spin-weighted spherical harmonics, right? And this you could call some, so this is a trivial operation, just changing basis from theta and phi to L and M. To leading order, even to leading order in Pm for generic velocities, no closed form expression for these guys is known. But again, when you re-expand for small velocities, of course, as you already know, the quadruple dominates and so on. So what I wanted to say is that all Lm contribute even at leading order in Pm, but then, of course, low Lm contribute for Pn, so if you want for small Pv. This surely is well known to everyone. Okay, so now let me switch gears, as I was mentioning. Let me instead now consider the a scenario which is different. Now, here the two objects were far apart in the sense that we specify, so B much bigger than the typical size of the curvature, BM1 and BM2. Instead, here I'm in a scenario in which M, one of the two black hole, the object masses is much bigger than the other one, and the other one is just a tiny probe. And eventually we will consider it to move along a scattering geodesic, so a hyperbolic-like geodesic on the background of this object, but to leading order, the metric is just what you imagine, the Schwarzschild metric. Just a matter of notation. It's going to be 1 minus 2m over r, and m is going to be g times the mass of the black hole. And here I'm in a situation in which I'm a bit embarrassed because I'm in front of the world experts on applying the perturbation theory, and so I'm explaining to them the perturbation theory. Apologies, but bear with me. Hopefully at the end I will say something slightly newer. So it's very convenient to consider some Penrose tetrad. It will be helpful to study the equations for the perturbations on this background. There's going to be an outgoing and an ingoing null vector defining this Schwarzschild coordinate, and some m angular vector that essentially plays exactly the same role as these epsilon plus or minus over here. I over sine theta, and its friend with the complex conjugate. So the approach taken by Tukowski to study the equations for the linearized perturbations on top of this G mu nu. So let me consider now another letter, G equals to G mu nu, now the Schwarzschild metric plus the perturbation. We want to study the Einstein equations for this for the metric, even in this expansion. So there's going to be a complete Einstein tensor, which is going to be the unperturbed one, which is simply 0 because Schwarzschild solves the homogeneous Einstein equations plus the first correction, and so on and so forth. So eventually the equation I'm going to solve is of course delta G mu nu equals to 8 pi G, the stress energy tensor that is simply given by this particle moving along geodesic. So spell it out maybe once. Mu, the mass of the probe, square root of G, integral delta 4. So this is calculated at x minus x of tau, tau being the proper time with respect to the background. Voilà. So, and then in principle there is a straightforward setup to consider, in addition to particles minimally coupled to gravity, which I'm going to focus on for simplicity in the presentation, to consider also electrically coupled and scalar coupled particles. This is all in the paper. Let me not crowd the blackboard with even more equations than I will. So the greening strategy of Tukowski was to focus on the wide scalars, size 0, which is L, is a specific component of the wide tensor picked up by contracting in this way with the Newman-Penrose tetrad, and similarly. Similar to psi4, roughly we can think of this as the ingoing and the outgoing wave in a sense that will be very precise in a second, and to consider as a dynamical variable that we will soon expand in a way very similar to what we did for the wavefront infinity in terms of mode. By the way, often I will probably omit this integral and sum to spare a bit of time. What? Well, introduce a new label S, and for S equal to -2, we are going to consider r to the 4 times, say, 4, and rest to minus 2, we are going to consider just c0. Is equal to plus. The beauty or the useful feature of this choice is that then the Einstein equations written up there decouple. And one is left with the following. We can do using some notation. S of r. This is yes, data being r. R then yes plus 1 r plus omega divided by delta. Almost there. Okay. So the Einstein equations read omega O S are equal to something that I will not spell out explicitly, but is essentially a source constructed from the T mu nu, well, T alpha beta over there, by applying suitable differential operators following Tolkowski. And so the job is being considerably simplified since we went, of course, from a set of partial differential equations that were all coupled to each other to decoupled equations. So S plus 1 and S equal, sorry, plus 2 and S equal minus 2 are the two versions of this equation that hold for these two variables here. They don't talk to each other, and it's an ordinary differential. So, of course, since we all learn in our elementary courses, when you have an homogeneous equation, it's a good idea to start looking at the homogeneous equation. And again, apologies for the experts. This is an interesting equation. This is a connection different branches of physics, because it's a Compton-Cohen equation with regular singularities at r equals 0 and r equal to m, which is the position on the horizon, if you want, and an irregular one at infinity. So, and therefore a lot of techniques have been developed to study it. We just chose one that was suggested to us by our collaborators, which have particular work on this very recently, and we try to sketch it in a few minutes. Maybe what I wanted to mention to start with is that the first thing that you can start doing with this equation is to look at it in two asymptotic regimes. So one can study what happens for r that is close to infinity, and one quickly realizes that, of course, two branches of solutions that look interesting. Let me denote them by r plus infinity and r minus infinity. These are, if you want, the purely outgoing and purely ingoing solutions at infinity. The first one, r plus, which is the purely outgoing one, goes like this. And r star is, of course, the regardless coordinate. And the ingoing one instead. And of course, the reason why we call them outgoing and ingoing, it will be apparent in a second, is that when we go back and plug this back into the Fourier transform, of course, this recombines as the advanced time, and this recombines as the reactive time. So they describe radial perturbations that move outwards and inwards. And a similar analysis at the horizon identifies instead the purely ingoing and purely outgoing mode there, with a characteristic lack of fantasy, let me call them plus and minus 8. And the behavior is the following. So now R tends to 12. This is the outgoing guy, and this is the ingoing guy. So for latent convenience, let me introduce a specific choice of normalization for two of them, in particular the purely outgoing at infinity and the purely ingoing at the horizon that will feature eventually in this calculation of the waveform I promised you. So we'll denote R in, the guy is, there's a coefficient that I'm not telling you, but can be written down much more explicitly, times this R minus H, so it's purely ingoing at the horizon. And then, of course, when you want to rewrite it in terms of a linear combination of the purely outgoing and ingoing guys at infinity, involves some non-trivial, some other nonlinear coefficient, which we fix as follows. So in particular, we find it convenient to fix the coefficient of these guys, you can see, and similarly for R up, which is instead proportional to R plus at infinity, and is going to be instead we involve this as some D coefficient that I'm not telling you right now, but as a fixed coefficient in terms of R plus. Of course, from this solution we can construct the so-called Wronskian or Wronskian rescaled by delta ds plus 1. Which is constant thanks to the fact that it satisfies the homogeneous Minkowski equation and is proportional to these B and A guys. Okay. So assume for the moment that in some way we are able to have a handle on the explicit expression for this, and we come back to this in a second. Why do we care? This has nothing to do with the original problem. So the reason is that there is a neat way of constructing the solution of the homogeneous, the inhomogeneous equation from the solution of the homogeneous equation, and in particular the formula for the retarded solution is the following. Let me omit omega for simplicity. Plus R in and then the rows of R up and intercheck. So it's an easy exercise that you can do later on when you're feet in some cold water, want to relax, to check that this satisfies the equation written over there in the box. So how do we see that this is actually the retarded solution? Well, we should check that since we have prepared our system in such a way there is no incoming radiation, this guy should be both purely ingoing at the horizon and purely outgoing at infinity. And this is indeed what happens. You can easily convince yourself, for instance, let me do the easy case first. Suppose we are going to consider R close to 2m, since, as I was mentioning, we are focusing on a situation in which this trajectory is something like this. There is an R mean below which t is exactly 0, right? For any R prime smaller than this radius of closest approach, so clearly the first line is exactly 0, and then clearly the solution is purely going at the horizon. So explicitly the behavior is the following: delta minus s valuing to m e to the minus r star, and then something that we may identify as a coefficient characterizing essentially we will see the waveform close to the horizon. We'll be a bit more precise about this in a second, which is this integral which we now extend from 2n to infinity. There we go. The opposite exercise is slightly less trivial in this case because Now let me try to play a similar game. Let me try to take R very big. So if we were in a situation in which this motion remains bounded, then we would be able to say, aha, since there is an R mass above which blah, 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 the second line is exactly 0. For the scattering, this is not obvious. So let me focus on an easy case, which is the one in which R is smaller than 0. So in particular, this we hold for psi 4, whereas for psi 0, there is an asterisk that I'm happy to chat about later. So for S smaller than 2, it is easy to see that indeed this second line is subdominant corresponding with respect to the first line. And the behavior is the one you would imagine. The ion star divided by R, the 2S plus 1, at zeta infinity, z infinity, which has the only difference of being evaluated with R in. So this is, in a sense, this is the main point of this derivation, why I went in some detail. The main message I wanted to convey is that if you are very well versed in Black-hole perturbation theory, as many of you are, calculating the waveform at infinity and calculating the waveform at the horizon is basically the same thing, except that you have to replace this R in, which would be relevant for the one at infinity, with R out.
So you can, I'm a bit confused. So A and B are equal. Is this?
Yeah, this is a consequence of the fact that the Wronskian is constant. So you can evaluate it either at infinity. It's essentially the same as when you solve the Schrodinger equation and have some constraint in terms of the unitarity of the wave function, right? So
Yes, yes,
A squared plus B squared is equal to 1, so it is similar. Yeah. Okay, so then the rest of the talk is going to be some computational mess in which I want to derive for you the first non-trivial example of this calculation in the case of this scattering I was talking about, and write for you an explicit result. So to do that, the first thing is that this expression, you remember I said this is constructing from the T alpha beta, but there are some differential operators that you can look up in Tolsky. The name of the game is to integrate by parts all of them and let them up this R in such a way that then you can use the delta function that appears inside of this guy. The end result of all this, blah blah, I said in words, is the following. There are some of some coefficients that you can look up in the paper. Maybe I write a sample, and then some operators that act indeed in this are in up. And then what is left to do is to perform this integral, which is essentially an integral over a trajectory. For instance, in the case S equal to plus 2, so the one that will be relevant for eventually for psi 0, so for the thing close to the horizon, I don't know, B1 LM is just a bunch of factors, and then Y1 LM evaluated at pi over 2, 0. So these are just some numbers that depend on LM. And instead L1, calligraphic L1 is IG, L would be the angular momentum of the geodesic. And then, okay, yeah, let me not write it in complete detail, but at some point it involves a derivative with respect to R, just to give you a flavor of. These are not very complicated, they are just some polynomials in derivatives. As you can imagine, they go from 0 to E. In the case of gravity, the one with I equal to 2 equals 2 derivatives. Instead, this one involves only one derivative. Okay, so the calculation is the one outlined by this formula. But okay, I was already referring to these zetas, z as the waveforms infinity and the horizon. Let me try to justify this a bit better.
And you say light depends on the geodesic motion that you're considering, right?
This expression here, yes. As you can see, I already
the box thing, no.
The box thing, no. It's generic for a generic TLM.
But
That's right.
But for any TLM, you get just different lights, but you can always do the integration of R.
I'm not sure, because, okay, if you take a very complicated source,
No,
a very complicated
okay.
integral, right?
Right.
So this form is generic, but then when you have to specify the form of this TLM to actually perform this step explicit. So what we have performed explicitly is for the geodesic I was sketching.
So this unbounded.
Unbounded, well, actually generic, I would say generic geodesic on Schwarz. Okay, so what we actually mean by waveform is what I said at the beginning, right? We are actually focusing on the h mu rather than psi 0 and psi 4, so let me at least sketch the connection between the two. I mean, conceptually it's kind of evident, but let me be precise. So at infinity, the conventional thing to do is to introduce this retarded Bondi gate. I can be more precise if you want to, but okay, let me justify it by saying this name, which is hallowed and loved by everybody, and then what I claim is that the connection between psi 4, this is a very well-known relation by the way, is that in this limit, at fixed u, the relation between psi 4 and the waveform is the following, where h is nothing but the contraction of h alpha beta with n bar alpha n bar beta. So it's literally the contraction with epsilon minus, if you remember what you wrote a few blackboards ago. So then, okay, in my notes here I had a completely nonsensical proposition of actually going through the whole steps, but I mean it's completely clear that you substitute here the mode decomposition of H, you substitute here the mode decomposition of psi 4, the mode decomposition coefficients that I was calling W for H, and the mode decompositions for psi 4, which we call here Z, are proportional. Let me just write down the proportionality constant because otherwise it would be too much. We are also very tired. It's kind of late. So this is the connection. And this, in fact, had been already used in a previous paper by Rodolfo, Francesco, and Francisco, who had explicitly worked this out. So for the case of psi 4, so this minus 2, sorry, this minus 2 is reminding us that this is related to psi 4, the mode decomposition of psi 4. There we go. So indeed, as promised, if you calculate Z, you have the waveform in the standard sense. Now what happens at the horizon? Well, as you can imagine at the horizon, the rows are basically interchanged. Instead of having a nice relation between the waveform and psi 4, there is a nice relation. So at the horizon, at H, you can impose an advanced Bondi gate. And the nice relation is the following: psi 0 is as r tends to 2n for fixed v. By the way, u here now is t minus r star, right? The tortoise coordinates, and similar here v is t minus plus r star. The relation is the following. Where h bar is, okay, h alpha beta contracted with m without the bar. So again, if you go to mode decomposition, you get a nice relation between the mode coefficients of psi 0 and the mode coefficients of h bar, which is the following. Just that this dV pulls down an I omega from the written sum of course. There we go. So this is the reason why I've been calling them waveforms at the horizon already over there. It turns out that in this, well, that the mode coefficients of psi 4 and the mode coefficients of psi 0 are not actually independent. There are identities that connect them, which are known as the Minkowski-Starobinsky identities. So there is actually an equivalent formula that you can write between the waveform at the horizon WH ln plus 2 and zeta h ln minus 2, which will be the mode coefficient of psi 4. And since we have two independent expressions, well, formally independent expressions in terms of these operators that lead to a technically different calculation from psi 0 and psi 4, what we did was to perform the calculation in both ways and check at the end that they give the same result at the order we're interested in. So let me maybe write here something like, you could also use psi 4. Thanks to this Minkowski-Starobinsky. So in the last few minutes, now let me go back to the problem I I postponed earlier on. So, okay, to actually perform this integral, you need to massage TLM in the way I sketched here, but you also need a sufficiently explicit representation with this R up and R in, and here we introduce an additional approximation. So we consider a combination of the two approximations I said at the beginning. So we consider not only M black hole to be much bigger than the probe limit, but we consider also the geodesic to be very, very far from the black hole. So we work both in the small mass ratio limit, so probe, and in the PM expansion. So GM, or M over B is also going to be small. And we're going to work to leading order in M over B very small. This has two simplifications. The first one, which is kind of obvious from here, is that instead of working with the full expression for the geodesic, leading order is enough to work with a straight line, because if this geodesic is very, very far, we just pretend it's on a straight line, and this is going to be enough to get the leading order, as we'll show in a second. And the second approximation is that we only need this R up in a certain regime, which is the following. So now, of course, I erase it, but you have it in your notes for those of you who are taking notes, which is, you remember, the contribution depends on M omega and, of course, on R. So since M contains G, and G is basically the parameter of our Cosminkowskian expansion, we are clearly in a regime in which M omega is much smaller than 1. So this is the first approximation. And then what we have to do is to solve this homogeneous equation using essentially the well-known methods of matched asymptotic expansions. So here I wanted to go back to something that maybe Rodolfo sketched, which is the fact that in this setup we need to consider several regions for this asymptotic expansion. Let me try to sketch it very briefly in pictures without equations. So consider R. Here, of course, we are at 2m. That would be at infinity. So in terms of length scales, let me say that omega is over the 1 over lambda. We said that we want to consider m be much smaller than lambda, so let me place lambda somewhere over here. And then, depending on the region that we are taking R in, we can expand our equation in different ways, of course. So there's going to be an interior region where R is, of course, a little bit bigger than 2m, because otherwise we would be falling in the code, but it's much smaller than lambda. So this is a regime in which you can expand the contribution in this way. And what the previous papers of Cipriani, Cheaton, Morales, Pogosyan did was to develop a nice systematic expansion, order by order in M omega, in this interior region that, let me note the two independent solutions identified by them schematically in this way. It's a sum over some object that order by order truncate to polynomials and the 2f1. I guess the leading order is very well known, but they gave a nice systematic setup to perform this contribution to high orders. We are only using the simplest leading order part of the result, which is actually well known. And similarly, in this instead exterior region, where 2m now is much smaller than both r and lambda, which could instead be of the same order, there is a similar expansion in terms of 1f1, very schematically. Yeah? And then the reason why I'm speaking about matched symptotic expansion is that, as you remember, we want to fix the boundary condition for this, say, R up in such a way as to be purely outgoing at infinity, but we wanted to have a specific coefficient in front of the outgoing solution at the horizon. So we need to connect these two regions. So what we have to do is to use this buffer zone in order to make sure that the R plus, say, that you're using here is going to be exactly the same as the R plus here. And since they have been chosen in such a way that they have the same monodromy around the point at infinity, this is it's a simple procedure because you just take the ratio and put it equal to 1. This kind of systematizes the whole procedure, and eventually the connection between these guys and the expansion close to the horizon and these guys and the expansion close to infinity is simple because it's just a connection problem of a hypergeometric function. It's very well.
Sorry, just please, if I understand. So this regime, M omega much smaller than 1?
Yeah.
So you translate it in when you are close to the particle or close to the black hole?
No, there are two a bit independent things that you have to do. So this is motivated by the fact that we are going to work to leading order in Pm, and the power counting parameter of the Pm expansion is the Newton constant. So this, okay, you want me to write this, Vm black hole omega. So this must be smaller, much smaller than 1. You remember, omega eventually is going to be of order 1 over b, as I answered to some of the questions. So this is, you know, oops, this is the Pm expansion, right? And then I'm just saying, if you want to solve your equation, you cannot just take m omega to be small and pretend that r does nothing, because then you would immediately land in this region. You have to keep the other region. Once you keep the two regions, you have two systematic expansion, you solve, and you claim victory.
Sorry, also more question, like, so you're doing the integral over R because you have this delta function, so now R in and R up are, for example, R in would be evaluated at R equal infinity, basically, like
No,
large
no,
R.
exactly. In principle, you could choose if
Yes.
you want to evaluate it here or there. But what I was about to say is that since we are creating a geodesic to be very far from the black hole, eventually the expression that we care about is the one in the exterior.
Exterior
Because
mean-
R is of order, is going to be much bigger than 2m, but generically of order 1 over omega or lambda. So let me write it down.
Okay.
The actual expression that we use is probably the simplest possible one. The only non-trivial thing is the coefficient in front. You have to fix using this matched asymptotic expansion. So it's nice to introduce this dimensions variable and probably one. So the leading order approximation in the exterior region for both R in and R out are as follows. R in is just proportional to the, so on the linear side. The leading order as x tends to 0 is some gamma function. Guy. So this would be the one that you need to calculate the waveform infinity. This is what Rodolfo and company did a couple of years ago, I guess, and check that matches perfectly the available results coming from all the other approximation I mentioned today, PM, PN, etc. And instead, the one that we need for our waveform at the horizon is this one. I promise it's the last long equation I ran. Or ish. Maybe let me simplify my life slightly and only write the first part and tell you why the second part actually doesn't really matter. Then there is another coefficient and another 1f1. But if you use the trick I was saying to calculate psi4, you can check that actually for some reason that we don't fully understand, I have to say, this second line integrates to 0. So this is enough to actually calculate the result. So maybe this answers your question. As you can see here, we are keeping the dependence on y, exact. So R is generically of order 1 over omega, it's a trivial function. But x, so m omega has been expanded out. So this is the expression in the exterior region. And the reason why we only care about this is that the geodesic over which we are integrating is precisely in this.
So you're keeping m omega small, but omega finite.
That's right. Generic.
Generic.
Okay.
Order 1, let's say.
Yeah, exactly. Generic order 1, and then, of course, there will be a region eventually in which the geodesic also goes very far, so it becomes big, but that's going to be essentially dominated by a soft limit, if you want, in which omega is over 1 over.
So you have to integrate the full average geometric, basically. That's the...
Exactly. Then what seems a bit cumbersome is that you have to integrate these guys, and they look a bit scary. And in fact, what I remember now, I go back to the comment I was making earlier on. If you want to calculate all the multiples at leading order in G, so you want to calculate the waveform at infinity for leading order in G, you have to deal with this guy for generic L, and you have to do all the calculations too. For fixed L, these guys reduce to actually exponentials times some polynomials and rational functions, so they're not that bad. but still you have to do all of them. And the reason is that, as you can see, they are suppressed by this factor here. So when omega is generic, the velocity is generic, omega r, this guy is generic, and you have to just keep all of them. They would be suppressed, so higher L suppressed only for small velocity, which correspond roughly to omega r. But for generic velocity, you have to keep all of them. Now you can see from here that the behavior close to the horizon is the opposite. So these instead are higher L's are suppressed by the PM expansion. So if you really care only about the leading PM order, you can just keep the leading L. So for instance, L equal to is enough for gravity to lead PM order. And for generic velocity. Okay, so with this, I think I gave all the ingredients. Let me write down, well, the result, or at least one result. So what we did was to actually use this formula to calculate this Z. As I said, it's enough to calculate them for L equal to 2. Let me know, okay, they are very similar for M equal to, say, +2 and -2 and +1 and -1. Let me give just some sample. Let me give 2, 0, -2. Just to show you that, okay, the result is very simple and explicit in the very end. Square root of sigma squared -1, so you see they depend on, in an integral way, on the velocity. Remember the sigma is related to the gamma factor of the two objects. So in this case of the geodesic, there is this kappa 0, and then there is a similar distribution with a kappa. There we go. This is the result, and then, okay, there is also M equal to plus, minus, and then plus or minus 1. You can look up in the picture. So in the end, the result, as you can see, is simple. If I were writing slightly smaller, it could fit on one line. And in a sense, it was a bit surprising for us for two reasons. One, because we didn't really expect these different systematics of the two expansions. And second, because as I remember, I said at the beginning, there isn't really an expression, a closed form expression for generic velocity for the waveform multiples at infinity. So actually calculating waveform as the horizon is much simpler calculating that. Okay, then cross checks, just to conclude. What we did was to take the absolute value squared of these waveforms, as you can imagine. This allows you to calculate how much energy and angular momentum falls inside the black hole. So we can use them to calculate the energy that is absorbed and the angular momentum that is absorbed. This is a tiny effect in the PM expansion. Due to the various powers of G that appear in the formula, it will be essentially suppressed by G to the 7, so again, tiny. But this for us is a nice cross-check because this has been already calculated in papers by Jones and Ruth, and also before that by Rothstein and Goldberger. So the expression we get for this is very simple, just because squares of these types of functions integrated over the frequency, mathematically I can do it for you very easily. And this guy instead is a new result that predicts how much angular momentum falls inside the black hole. So maybe let me end on this note, which is that even if you start with a Schwarzschild black hole and you scatter them, eventually you will end up with Kerr black holes for many reasons. A tiny reason is that some of the angular momentum that is initially mechanical angular momentum of the system will fall into the horizon and one of the black holes will start spinning. So thank you for your attention.
Thank you, Carlo, for a very nice talk. Are there any questions? We had some during the talk, but we can time for some.
Maybe I have a question. So, if you want to calculate a waveform at infinity, can you do it for large angular momentum?
Large L?
Yes.
I think it's one of the things we sometimes wonder, but we haven't. So, okay, maybe I should add one more point, which was a bit glossing over. So this expression I've written here, very, very nice and explicit. is actually not enough to calculate the leading waveform at infinity. And the reason for that is that if you use this expression and plug in the straight line trajectory with the leading order approximation of PM, what you would get is a result that does not depend on time. So this would actually give you just a Coulombic field, or if you want, the linear V-shaped analog in gravity of the potential of a particle moves along a straight line. So that's not a waveform, right? It doesn't depend on time. To see some time dependence, you need to go to the next order in G. So at the next order in G, this expression, I mean, you can obtain it with the method I sketched that has been systematized by Cipriani et al. Last year. So there is a concrete expression for the next order of the kernel, but you have to integrate that with the next order in the geodetic. So it requires a bit more work. But indeed, looking at large L could be one thing one can do in principle. Yeah.
Yeah, could you comment on the soft limit and then look at the horizon?
Right. Very good, thanks. So one thing that I think is apparent from what I wrote, although we should be careful because there are other factors of omega to connect the z's to the w's, but okay. So when you look at small frequencies, you need small frac u, essentially. So u is basically the frequency, apart from some factors that don't matter. So the leading order, this would go, k1 would go like 1 over u, so 1 over omega, but this is compensated by omega here. So there is no pole for small omega. This is in contrast to the situation at infinity, where of course there is a 1 over omega pole, which corresponds to the well-known memory effect, because the Fourier transform of 1 over omega pole is a permanent change in the value of the field. So in fact, this was important for us in the calculation of the angular momentum, because roughly the integrand for the energy absorption goes like omega squared w squared. So doesn't really care whether there is a time-independent component in W. And indeed, both these W's would go like 1 over omega at infinity, and this would go simply to a constant. Instead, the situation for the angular momentum is essentially like this. So it would seem to be in trouble because the thing diverges. There is actually a delta function. It's not 1 over omega, it's a delta function, and this means this signals a sensitivity of the angular momentum is related to infinity to this static mode I was mentioning. So the static component that you get to leading order in G. The situation here is much more simple. There is no pole, there is no sensitivity to any time-independent part, which would be like a delta of omega in frequency domain, and which would not be very easy to handle in this approach, because we work in a frequency domain and multiply and divide by omega all the time. So distributions in omega would be a bit complicated, but okay, we are. For this reason, precisely due to the absence of this 1 over omega pole, we are confident that there is no sensitivity to this static. So there is no pairing between a Goldstone mode and a memory mode, if you want, because there is no memory mode in the language at the same
And what
time.
about if you were to look at the more subleading order away from the horizon? Because one would expect that if there is a sort of, I don't know, there is such a thing of memory near the horizon, that it would probably come at next order.
Next order in R close to 1. I see. No, okay, we didn't calculate it there. We only calculated the leading order. Actually, okay, maybe I should never say overconfident things. But one thing that for me is very exciting coming from amplitude is that amplitudes are very nice only at infinity, because of course they work with asymptotic states, and so you can only ask questions about what happens to leading order in 1 over R. I mean, this is the easiest answer. The easiest things to ask from amplitude. Instead, this formalism seems, to give you much more control, right? Because you can, in principle, calculate it a bit everywhere, and then, okay, of course, it's gonna be harder, I agree, but it doesn't look really hopeless. If you want to calculate the field somewhere else, it's gonna be more work, but in principle, it's, you have concrete expressions that you can write down, and then maybe performing integrals can be harder to get a very nice analytic expression, but in principle, the answer is under control, at least formally. Maybe let me add one more word, though, let's say motivation, why one should care about any of this. It's just an exercise after all. One thing that is a bit of a puzzle is that if you take any of these answers that I wrote down for the absorbed and energy angular momentum, but also for the ones emitted at infinity, they seem to be very badly behaved when this sigma tends to infinity. So this is, I guess, one of my motivations for looking into these complementary methods to amplitudes, to understand what happens when these derivatives become null, actually, which connects in some sense to a lot of things have been said about non-geodesics or going in different contexts.
Any other questions?
Maybe I have something was wondering. So R up, that is
Yeah.
the thing that you okay. This is the wave function that is purely outgoing at the horizon, right?
No, purely outgoing at infinity.
Sorry, indeed, sorry. Purely outgoing at infinity.
Yeah.
And you're evaluating it in this near zone, like in this
In the exterior zone.
In the exterior zone,
Yeah.
yeah.
Because just because this integral, as you can see, it's formally from 2m to infinity, but this t is localized where the geodesic actually is, and we are taking a geodesic that never goes close to the horizon, right? Because we are staying in this, okay, I raised it, but in the PM regime, which is when r is much bigger than 2m, but okay, generically of order 1 over omega, which is exactly the regime in which x is small, but y is generic.
One thing I'm a bit confused about, so shouldn't you have also a term that goes like x to the minus l?
X to the minus m,
L.
l.
Maybe I'm,
Maybe second one? No, I don't think so.
because you
In our up,
yeah, because you go from, maybe I'm a bit biased from what I,
if you want to read the expression I didn't write, is this one. But there is no such term, right? Just y, there are some different y's in the second term that I omitted, you see here. So there is a y to the 2l plus 1 for the rest of the argument, but there's no x.
so everything is, okay.
So just because we are expanding for small x, so this, I am claiming that this is the leading order in x. If there were to be another term in x, it would be subleading. Say if it were to be plus x to the.
So the full solution, because it seems weird, but well, maybe it's a curiosity, we can talk about it after, but like maybe just let me say why I think it's, so the full solution is subleading, is, I mean, higher L is as smaller, like for the full solution. It's not like some things are smaller. Like R up is
Yes.
suppressed at the higher speed.
The contribution to the exterior zone, evaluating the exterior zone.
but
So in for
I mean,
this,
if you take, I mean, R up is over the x to the L, right?
plus 1 minus.
Yes, but so like if L is twice, like if L prime is twice, then the full R up becomes like smaller,
Yeah,
suppressed
yeah.
to x.
And then on top of that, there will be, I don't know, plus x times something else, plus x squared times something else.
Yeah,
But what I'm saying is that for any L, this is the leading contribution.
So basically what happens in the PN for the wave for infinity, here happens for the, as Carlo said, for the PM at the horizon.
It's exactly the same for the, is what we're saying, for large, at infinity, for any L, this is the leading contribution in X, but it's not suppressed by L. You can only truncate in L if you assume that Y is small, which corresponds to PN.
So it's just it seems that it's some normalization, no? X to the
The normalization is fixed by the match asymptotic expansion.
No, but it's a constant, an overall constant.
No. Now it's fixed because this is the solution of the inhomogeneous equation. There is no ambiguity. Operator acting on R equal tau, T mu nu. There is no constant.
Okay.
If it was just the homogeneous solution, I agree. Because of course it's equal to 0. If you multiply by a constant, it's the solution.
Maybe
But this is the solution normalized in the way that I wrote. And this is the one that gives this. So I try to be precise about. So these wiggly lines are not up to factors. They are actually asymptotic equalities
maybe these are
with the factors.
Okay. Thanks. No, this settles.
Okay.
Any final questions?
If the chair asks like that.
Sorry. Further questions. Otherwise, let's thank Carlo again.